All right, we need to finish up 4-1 day 2. There's only one example left in there, so we're going to call this 4-1 day 2, which we have one example, and we're going to start 4-2 and spend 2 days there. So this section will be labeled 4-2 day 1 and 4-1 day 2 and 4-2 day 1. So finishing up 4-1. You're going to have problems that ask you to find the expected value. So just vocabulary, expected value of a probability distribution. All that is it's the mean of the distribution. So when they say expected value, it just means mean. Why do we need two words for the same thing? I don't know. So the expected value of a probability distribution is the mean of the distribution. And if you remember from yesterday, to find the mean, which we're going to call the expected value, you're going to sum up each x value multiplied by its corresponding probability. Okay, so our one and only example. Let's say there's a raffle that's going to sell 1,500 tickets at $2 each. Can you find the expected net gain for one purchased ticket? Okay, so expected value is the mean, and so what we are looking at is the net gain. So, and here's the raffle. There is going to be one $500 winner, two $250 winners, one $100 winner. There are going to be five $50 winners. So what we need to make a table of is the net gain. So X is going to represent net gain. And then we're going to look at the probability of that net gain. Okay. So when I buy my ticket, I have a chance of getting this $500 prize. So what's my net gain? Net gain means I got to take off what I put in. So my net gain, if I win the first prize, is $498 because I paid $2 for my ticket. And what's the probability that I gain $498? Well, it's 1 out of 1,500. One ticket out of all of them is going to be worth that. Okay, maybe I don't win first prize. Maybe I win one of these $250 winners. Well, 250, I paid 2. My net gain is going to be 248. And because there are two of those, two winning tickets, I got a 2 out of 1,500 chance of winning. The $100 winner means I've got a $98 net gain, and I've got a 1 in 1,500 chance of winning that. The $50 winner puts me at a net gain of $48, and there are 5 of those. And then there is one other option for me. If I don't win one of those, I win nothing, but my net gain means I lost my $2. That's a -2 net gain. And the chances that I lose my $2, well, I got to see how many tickets are losers. So there's 1, 2, 3, 4, 9 winning tickets. So 1,500 minus 9 means there are 1,491 losing tickets. So I got a 1,491 out of 1,500 chance of losing my $2. So now it's net gain. Now the calculator does all the work for us. So I'm going to take the time to put those into list 1, which I should have done quick earlier, but 498, 248, 98, 48, and then a -2, and now the corresponding probabilities. 1 out of 1500, 2 out of 1500, 1 out of 1500, 5 out of 1500, and 1491 out of 1500. Okay, now I'll come over. List 3, I will multiply those two lists together, and then I need to sum those up. And I will go under List, Math, Sum L3. L3. So my expected net gain, which is my mean, is a -1.1, and since we're talking money, I expect to lose $1.10 for every ticket I buy. Okay, and that finishes up section 4.1. Okay, moving into 4.2, we're going to talk about a special probability distribution. It's called a binomial probability distribution. So, the binomial probability distribution or experiment. Okay, to be binomial, 3 things have to happen. Each experiment is repeated for a fixed number of trials. So you know exactly how many trials you're doing. Number 2 thing that has to happen, on each trial there can only be 2 outcomes. That's the bi in binomial meaning 2. So each time there are only 2 outcomes. And your 2 outcomes are success and failure. And then the 3rd thing that has to happen is that the probability of success has to be the same for each trial. Must be the same. So if any one of these things isn't happening, the situation is not considered binomial. So when we go through, there's going to be a formula we're going to be using. N is going to represent the number of trials you're doing. P is going to represent the probability of success. Oops. On each trial. Remember, it's got to be the same for each trial. Q is going to be the probability of failure on each trial. Ditto means to look at the word above there. And then X is going to be the number of successes you are looking for. So let's take a look at a situation and decide if it's binomial or not. And if it is, I want you to be able to pick out N, P, Q, and X. So So example 1. Question is this a binomial experiment? There's our question. Is it binomial? Here's the situation. You are going to take a 10 question multiple choice test. Each question has A through E for options, and you're going to be looking for how many you get correct. Okay, so first we'll go through it. We're trying to decide if this is binomial. The very first thing I told you was that the experiment had to be repeated for a fixed number of trials. So do I know exactly how many times I'm repeating something? And the answer is yes. Each question is a trial, because I'm guessing on these, and we're probably looking for how many I get right. So I am going to guess on 10 different questions. So number 1, yes, I know exactly how many trials I'm doing. Might as well write it down. 10 trials, each question is a trial. Are there only 2 outcomes each time? Success and failure. Well, think about a question. I either get it right or I get it wrong. Every time I either get it right, success, because I'm looking for how many correct, or wrong. So yes, there's only 2 outcomes. And then, is the probability of success the same on every single trial? Well, yeah, what's the probability I get the question correct? Well, it's going to be if it's A through E, A, B, C, D, E, that's 5 options. Only 1 letter is going to be correct, so I got a 1 in 5 chance, 1/5 chance of getting each one correct. So this is binomial. So yes to binomial. So we'll finish up. Q then is the probability of failure. Well, if there's 1 question correct out of 5, that means 4 out of 5 are going to make me fail or get it wrong. And then X. X is the number correct. Well, what values can X take on? Well, X could be any number. I could get 0 correct. I could get 1 correct, 2 correct, 3, 4, 5, 6, 7, 8, all the way through 10 correct. Can't get 11 correct. I can't get a negative number correct, but any value between 0 and 10 is what X could take on. And we're going to be looking at probabilities. Well, if I guess on all 10, what's the probability I get 2 correct? Or what's the probability I get at least 5 correct? Questions like that are coming to you in the future here. So what's going to help us figure out those probabilities is the binomial probability formula. So the binomial probability formula the probability of getting exactly X successes is given by this formula. P of X equals NCX. N is the number of trials, C is their combinations, X is the number correct, multiplied by the probability of success raised to the number of successes power, multiplied, is there time? Maybe I'll do dots instead, by the probability of failure raised to the n minus x. So it's a plug and chug formula where we need to know the number of trials, the number of successes, the probability of success, and the probability of failure. So let's go back to, which one am I going back to? The one I just did. Let's go. So example 2, we're going to use example 1 that had the 10 question multiple choice test. So 10 questions, each one is A through E. Can you find the probability of getting exactly 6 of the 10 questions correct? No more, no less. So my number of successes I'm looking for is 6. So I'm looking for the probability of 6 successes. Okay, using my formula, I need the number of trials. I'm doing 10 trials. C, X is my 6, multiplied the probability of success. So each question, there was A through E. I've got a 1/5 chance. So I can use 1/5, I can use 0.2, whatever you want. I've got to raise that to the X, which is 6, multiply by the probability of failure, raised to the n minus x, so that's 10 minus 6, or 4. And then it's plug and chug through the calculator. And I'll just show you one real quick. So, got 10 NCR 6 times 1/5 in parentheses raised to the 6 times parentheses 4 divided by 5 raised to the 4th. 0.0055. So less than a 0.5% chance that I get 6 correct. Exactly 6 correct. Okay, let's try another one. Number 3. Let's see, 71% of retired workers rely on their Social Security to survive. I'm going to randomly ask four retired people, do you rely on your Social Security and we are going to make a probability distribution for those that say yes. I rely on Social Security. So let's make sure this is binomial, and we'll pick out all of our values, the n, p, q, and x. And remember, a probability distribution just shows all possible number of successes. So it's a whole table we'll be making. So first, am I repeating this for a fixed number of trials? And if you read through here, right here, I'm going to ask 4 people. They can either tell me, yes, I rely on Social Security, or no, I don't. I've got investments that I don't need Social Security. So it's success and failure. They either do rely on it or they don't. And then the probability of success, I got a 71% chance every single time I talk to someone. So it does fit the binomial formula or criteria. So n is 4. Probability of success is 0.71, 71%, which means our Q value, P and Q, remember, have to add up to 100%, success and failure, so it's 1 minus 0.71, which is 0.29. And then X, the number of successes. In other words, how many people could say, yes, I rely on Social Security? Anywhere from 0 people could say they rely on Social Security, or 1, or 2, or 3, or all 4. I'm only asking 4, so I can't have anything higher than 4. So our table we're going to make, our probability distribution, is the whole table, has X values that go from 0 to 1, 2, 3, and 4. So our formula, the P of X, so if X is, I'll go with 0, I've got first 4, C0, times the p-value, which is 0.71, raised to the 0, times the 0.29 raised to the n minus x is going to be 4 minus 0, which is 4. So now I will start that. I'm going to show you a slight shortcut. So we got 4 NCR 0 times 0.71 raised to the 0 times 0.29 raised to the 4th. So that probability is 0.007. Now if you do second entry, entry is right above your equal, second entry, that retypes that line, or some of your calculators let you just arrow up and retype over, but just retype over the numbers. The 4 isn't going to change, that's the number of trials, but now I want 1 success, so that's going to change this 0 to a 1, and then the 4 is going to be a 3, because I do 4 minus 1 for 3. Remember, the two exponents are always going to add up to your sample space. Hit enter, 0.069. 3 more times. These get to be a little long, that's why they won't give you too high of a number here on these ones. Now I want 2 successes, 2 successes, and then I'm doing 4 minus 2 for 2 there, all 2's all the way through. 0.254. And then 1 more time. Oops. 3 successes, 3 successes, 4 minus 3 is 1, 0.415. You can see with that high probability, I'm getting much more chance of getting a greater number of successes. And then our last one. I want all 4 successes, 4, and then a 0 here. And then the last thing we're doing in this section is finding the mean, the variance, and standard deviation for a binomial distribution. Now we could go back and use those formulas from 4.1, but for a binomial we have some shortcut formulas, but only if it's a binomial distribution. So, shortcuts. For mean, variance, and standard deviation of the binomial distribution. Okay, the shortcut for finding the mean is just to, remember the symbol, multiply the number of trials times the probability of success. Shortcut for variance is n times p times q. And then again, standard deviation, that same relationship exists where it's just the square root of the variance. example 4. Can you find the mean, the variance, and standard deviation for example 3, which had the retired people in it? So, to get the mean, I need the number of trials. I bring this in. I was doing 4 trials. Probability of success on each trial is 0.71. So the average number of successes I would expect is 2.84 with a variance of 4 times 0.71 times 0.29, which comes out 0.824, and that would be people squared, and then the standard deviation will be the square root of that, which is 0.90.